Hello and welcome to another measurement and instrumentation class. In the previous class, we went through complex power. What is complex power, real power, reactive power, and the way that we calculate real power and reactive power, and the relation between real power, reactive power, and apparent power, and also power factor and the power triangle. So these are mainly the ones that we solve are for a single phase system. Today we will start with three-phase power. You're already familiar with some of the concepts that I'm going to talk about today, but this is very important. I have to do a quick review and reminder of it. And after that, we will start with the measurements of power in a three-phase system. So before we go to the measurements of three-phase, we will go through the concepts of three-phase power and the different ways that we connect a three-phase system. We have a Y or delta connection in a three-phase. The relation between the line and phase voltage and line and phase currents in a Y and delta connection. The relation between power in a three-phase delta connection and a three-phase Y connection. What are the difference between their phase power and their torque? And finally, if we have time, how we calculate the three-phase apparent power using the line voltage and current and phase voltage and current as well. So without further ado, let's start with it. So three-phase power. So power is generated in three-phase because it is more economical than single-phase. A three-phase alternator is constructed as shown below. The reason that we use and you can see here the phases A, B, and C, the three phases that we have. This is a simple three-phase motor. And the other side of the connection, which are the A prime, B prime, and C prime connected. Now, the reason that we even use the three-phase system is because of its major advantages that it gives us compared to a single phase. A three-phase power system can transmit more power for the same amount of wire, around twice as much as a single phase. Why twice as much? Because in a single phase, you need a neutral and a phase. In a three-phase, you just need three phases. You don't need a neutral. And I'll explain why we get rid of the neutral. So if I want to convert the same power with three single phases, I need to have three pairs, three phases and three neutrals. Therefore, I need 6 wires. But I can transmit the same power just by using 3 wires in a three-phase system. Now, the other advantage is the torque produced by a three-phase machines are constant. Three-phase machines use less material for same power rating, and the three-phase machines start more easily than single-phase machines because of their initial torque. Now, I have experience on doing a lot of repair and buying motors for different industrial applications. And I'll give you an example. A 10 kilowatt single phase motor would be around, let's say, $1,000. The same power, 10 kilowatt three phase, would be $600-700. So when it gets above 5 kilowatt, you most certainly need to go to a three-phase. So up to 5 kilowatt, they are probably the same price. But when it's over 5 kilowatt, it gets much bulkier and larger. And you most definitely have to go to a three-phase. because when you have less material, the motor will be smaller. Less material means less copper. Copper are expensive, and you're going to end up with a smaller motor. And the other problem is you don't have any added benefits. When you go higher than 5 kilowatt, you need a very thick wire to bring that power. You need like a 40, 50 amp single phase, which most certainly you can't find it in most places. So after 5 kilowatts, it's usually you jump to a 3-phase. Now you may ask, why 3-phase? Why not 4-phase or 5-phase or 6-phase? What we can do is we can have another 3-phase and put it in between the other 3-phase. So now we have 6-phase, and we're going to double the power again. So it turns out there is an economic and there is a technical part. The thing is, when you double the amount of wires, you don't necessarily double the power. And the other problem is you're going to put much more wires, the transformers, the transmission lines, the insulations. It's going to get very complicated. The distance between the wires, when you double the amount of wires, would be halved, and therefore you're going to induce a lot of reactive loss on the system. It acts like a big coil. But there are other reasons for that as well. I'm going to put this actually as a homework to do your research on why we use 2-phase or 4-phase, why we settle for 3-phase, why not use 4-phase. I'm going to give you actually this as a homework so you can do a research, and it's going to be an interesting, survey. You can write 1 or 2 pages about the reasons that why won't we use 4 or 5-phase and why 3-phase is going to be optimal. The reason that we don't use 2-phase because the phase difference between the angle is 90 degrees. It's going to be, 180 degrees. For 4-phase, it's going to be 90 degrees, and there are going to be some technical difficulties over there. Now, 3-phase power, a voltage is induced in the coils as the exciter field rotates according to the equation. V is going to be M, the d phi over dt. And we have different type of 3-phase motors, like the squirrel cage motors, the asynchronous. Even we have type of 3-phase motors that use permanent magnet, which I usually use in high power application or generators as well. Most of the times you can use a motor as a generator, and a generator could be used as a motor. Depending on your application, you may want to have a permanent magnet. This one has a permanent magnet, but you can even ditch that and use a solid coil like a squirrel cage system. And sometimes there's a trade-off on price and performance. If you use a permanent magnets uses rare earth material that are extremely expensive. So it's only beneficial when you want something very high performance with minimal loss. The difference between that and a normal AC motor that you see in a HVAC system, the difference between their performance and efficiency is about 3 to 5%. So 3 to 5%, if you're using it in an EV, it would increase your range by 5%. Sometimes it's beneficial because when you increase the bit by 5%, you can reduce your battery pack by 5%. So that offsets the price of the material that you put in. But sometimes if you want to use it, for example, in, a fan, it doesn't, justify the price that you put into it to get like 4 or 5% extra efficiency. And for that, nowadays we use brushless DC as well a lot. And I'll explain about that later on. If you're interested, I will explain about brushless DC, AC, and the difference. It's a topic of another course in power systems. Now, 3-phase, in the 3-phase system, we have 3 single-phase signals. They share the same voltage, or in other words, the same magnitude of voltage. They share the same frequency. Sorry. Okay. So they share the same magnitude. Let me highlight one with red. I'm going to highlight the other one with blue. I'm going to highlight the third one with green. So as you can see here, all of them share the same magnitude. VM is going to be the same. They share the same frequency. The only thing that is different between them is their phase. We have a 120-degree phase shift between each of the three phases. So imagine you have three single phase, all of them same voltage, same frequency, but a little shift in their phase. And when you add all of them together, 120 gives us a full 360 degrees. Now for this particular example, we use the American standard, which is a frequency of 60 hertz. And again, just a reminder, VAN is going to be equal to VM cosine of omega t plus phi. And omega is equal to 2 pi f. So if you put f as 60 hertz, you get an omega of 377. So for the first phase, it's going to be VM cosine of 377t. Second phase is going to be the same magnitude, same frequency, but a 120-degree phase shift. And the third one would be another 120 phase shift. Sometimes we show it with negative 240, or sometimes we show it with positive 120. Both of them. If you see it in some text like that, it's technically the same. Now, again, as mentioned, these are the phase shifts that we have, which are 120 degrees apart. We can also show this in phasor mode. We'll show it like this. VAN is going to be VM, which is the amplitude with the degree of 0 degrees. The second phase is going to be negative 120 degrees, and the third phase is going to be negative 240 degrees. Now, this graph shows the phasor. The vector, the length of the vector is our voltage magnitude, and the degrees are also shown here. For the first phase, VAN, by the way, VAN means the voltage between the phase and neutral, and I'll explain this. It's going to be VM with a degree of 0 degrees. VBN is going to be VM with a degree of negative 120 degrees. And so it's going to be from here to here. And VCN is going to be VM with a degree of negative 240 degrees or 120 degrees plus. So three-phase systems may be modeled by the voltage source shown below. We have two types of connections. We have the Y connection and the delta connection. Y connection, which sometimes showed with just capital Y. Sometimes we call it star connection as well. So if you see in a book that it's mentioning star connection, it means Y. Now a Y three-phase connection, as the name states, it looks like a Y. You have three-phase connected to a neutral. And in a delta connection, and it looks like this. This is a Y connection. And for a delta connection, you have three phases on a triangle like a delta. Sometimes they show it with delta. Y connection, delta connection. So a Y connection has a neutral in the middle. Delta connection does not have that. We will start with Y connection because the majority of the connections that we have is Y connection, and then we will move on to delta connection. So this here is a Y connected system. Again, you can see each phase, VLN, 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 same magnitude, same voltage amplitude, but different phase. And finally, the middle one is connected to the neutral. We can connect the neutral from the generator to the load side as well. That's the reason you see this neutral going out. But I will show you that it's not necessary sometimes. So the voltage shown in this picture are the line to neutral, meaning it's the voltage difference between each line or each phase and the neutral or the ground. Again, neutral is not always necessarily the ground. It's only with the ground when it's a balanced system. I'll explain about that. Sometimes we call this V phase as well, the phase voltage, or the phase to neutral voltage. So in some books, it's shown that way. Another way that we represent voltage is V line to line, meaning it's the difference. By the way, V line to neutral is the voltage difference between each line and the neutral. So between C and N, between A and N, and between B and N. Okay, VAN, VBN, VC. Now there's another way we represent voltage. This is between two lines or two phase. So voltage between A and C, voltage between C and B, and voltage between A and B. And we call that VCA, VAB, and VBC. Again, neutral is between one voltage and the ground. Line to line voltage is between, again, line to neutral between one line and the ground. Line to line is between two different lines. Now let's calculate and see how we can find the line to line voltage. There are a couple of ways that we can do it. We can use this graph and easily find the voltage, line to line voltage. Let's go one step back to, I don't know, this is maybe your high school math. We have two vectors, AN and CN, and I want to add these two vectors to each other. How can I do it?
Add their X and Y components together.
Yes. No. And what if so imagine I have these two vectors, for example. Do you remember how I added them? And this is vector A and this is B. So I will put an B here, mirror B, and I'll put another A here. So B and A. You remember? And this over here is going to be A plus B. Am I correct? Okay. So if you want to do that, I can add VAN here. And I have VCN over here. And adding these two, I have VAC. Okay, now let's find the magnitude of this and also the degree. We can easily do it. If I had the numbers here, I could do it. I can also have a proof as well. So now the voltage between C and A is going to be voltage Ln, or in other words, Cn plus Bn. Again, this is Cn plus Bn. Sorry, An. I want to do AC. Now, I can convert this to a rectangular form. Do you remember how we convert phasor to rectangular? So a phasor form, we show it like this. Let's say Z is R with a degree of theta. Okay. If I want to show it in the rectangular form, Z would be equal to A cosine of theta plus JB sine of theta. Okay. Or let me put it this way to make it easier. Z would be equal to R cosine of theta plus J R sine of theta. This would be my A and this would be my B. And this is the real part. Not to confuse you, this is going to be the real part. This is the imaginary part. Okay. Now, if I want to convert Z, the phasor, to the triangle, I would simply just replace it in the second equation. So, for example, here, if this is VAN with a degree of 10 degree, it's going to be VAN cosine of 10 degree. Or if I have, for example, R is 10 and this is 30 degree, Z would be 10 cosine of 30 degree plus J10 sine of 10 degree, 30 degree. So this is how we got from this to this. Now, how do we go from the rectangular form to a phasor form? If I have a rectangular form, Z is equal to, let's say, 4 plus J3, then R would be equal to square root of 4 square plus 3 square, and theta would be equal to what? Tan inverse of B over A. Okay, so for going from, I just want to let you know how we do that. If we are in the rectangular form, we cannot multiply a imaginary part to a real part. So if we want to do addition or subtraction, we have to go to the rectangular form of the complex numbers. If we want to multiply them, it's better to do it in a phasor form. Now here what we did when we added these two, real parts would be added together. So -1 minus 0.5 gives us -1.5. And the imaginary parts are added together. Now the imaginary part of this first term was 0 because sine of 0 degrees is what? 0. Therefore, J sine of that would be 0. So the first term doesn't have an imaginary part. Only the second term has an imaginary part. Now, when we added that, the final answer would be this. Now we want to convert it back to phasor. This is going to be A. This is going to be B. Therefore, R is going to be equal to A squared plus B squared square root of A squared plus B squared, which is going to be this square plus this square. And we get, and tan inverse of B over A. B is 0.866 minus 1.5. Now what we get is VCA is going to be square root of 3 VLN with a degree of 150 degree. So we're going to have something, it's square root of 3 and with a degree of 150 degree. Now we can do it for all the other ones as well. For VAB, again, we get square root of 3 VLN with a degree of 30 degrees. And for VBC, it's going to be square root of 3 VLN with a degree of -90 degrees. And if we add it here, you can see that we have 150 degrees. Or in other words, if I rotate it, I can draw it like this. It's going to be 30 degrees, 150 degrees, and the other one is -90 degrees. And this is going to be square root of VLN. This is the 30 degrees, 150 degrees, and -90 degrees. Now the important part is this. The magnitude, okay? Most times we don't care about the phase. We care about the magnitude. The magnitude shows us in a star connection or in a Y connection, V line is equal to square root of 3 V phase. So in a Y connection, keep this always in mind. V line is equal to, or V line, sometimes we shorten it, it's equal to square root of V phase. Or V line is equal to square root of V phase neutral or line neutral. And this is how we show it. And again, sometimes we show it like this. V line is equal to square root of 3 V phase. Now, let me give you an example. In a three-phase Y connection, in three-phase Y connected system, Y system, V line is equal to 380 volts. Find V phase. So V line is 380 volts. We want to find V phase. The magnitude of V phase, we don't care about the. Sorry? 548? Yes. What about the rest of you? Did you all get the same? What did you get? I'm sorry? Yes, that's correct. You have to divide it, not. So V line is equal to square root of 3 V phase. V line is 380, square root of 3 V phase. Therefore, V phase is going to be equal to 380 divided by square root of 3, gives us 219 something. I'm going to round it up. It's going 219.3 or 4 if I round it up. It's going 219.4. So keep in mind, V phase is always lower than V line in a Y connected system. So if you have a question like this in your FE exam and the options are, the choices are like 500, 450, 220, always keep in mind that V line is greater than V phase. So V phase must be smaller. Now, these are some common three-phase voltage system in North America. We have 208Y 120 volts, and we have 480Y 277 volts. Can someone tell me what is 280, 28 and 120, and what is 480 and 277? If you look on a plug on a three-phase motor, or you're gonna see these numbers. Can someone think of why do we show it this way? Let's do something. I want you to multiply 120 by square root of 3. (208), yes? So the number on the right is our phase voltage, and the number on the left is our line voltage. Okay. And again, I want you to multiply 277 by square root of 3. What does it give us? 480. Thank you. So again, the number on the right is the line to neutral or the phase voltage, and the number on the left is the line to line voltage or the line voltage. Okay. And since we have two different types of connections, Y means this is a Y connection. Okay. And let me go and show you something on a three-phase motor. Let's go to the diagram itself. Let me see if I can find one of them. Or I want to find a picture that. Just give me a second to see if I can. I'm looking for different pictures here. Problem is it's searching in Bing and I don't want to go on, Google. I think this one shows it pretty well. So on a three-phase motor, let me see if I can pull the picture here. Okay, this one doesn't show. Nope. Yeah, it doesn't show it on this either. Yeah, you can see here the voltages in the specification. The 208, 230 voltage, three-phase, the RPM and everything. But I wanted to see if I can find one that actually has all these information on it. Yeah, this one doesn't show it. I can show it to you in the lab when we go to the lab. But this is the way actually on a three-phase motor, the way that we connect and the voltage that is on a three-phase motor. I also have, if I can please have a moment of time, Y delta connection on a motor. So I just wanted to show you the difference between the Y and delta connection. In a motor, if you see that the motor has 6 terminals, you have 6 connections, that means that motor is capable of running on both Y and delta connections. And the way that we connect them, and I'll show you to you this in the lab as well. You connect U1 to W2, V1 to V1 to U2, and W1 to V2 or U2. And if you have 6 of these terminals, it means it's capable of running both on a delta connection and Y connection. And also, in addition to that, you would see that on the motor itself, it shows that this is like 480 Y 277, and it's also 480 delta. But not all motors are capable on running both on delta and Y connection. These are specifically made motors, and these motors require 2 sets of wiring with an open end so you could connect it and configure it however you want. Most 3-phase motors, you're usually constrained to just run it on Y. And I'll explain Y and delta connection and what is the difference between them. Before I compare a Y and delta, let's find out what the current is in a Y connection. So we found out that the voltage in a star connection, the line VL is equal to square root of 3 V phase. But what's the relation between the line current and the line voltage? Line current and the phase current. Why? Perfect, that's correct. If we do a closed loop over here, what you see is and by the way, this is the current of the line and the current of the phase. You can see that since these are in series, you can go from a single path, and therefore the line and the phase current are both the same. So in a star connection, I line is always equal to I phase. And the voltage of the line is square root of 3 V phase. Now, in a star connection, the total current what is the total current going to be? The total current would be the summation of each of the line or the phase currents. So it's going to be IA plus IB plus IC. It's going to have 3 different currents, IA plus IB plus IC. And according to the Kirchhoff's current law, I have 3 currents. I have IA, IB, and IC going in different directions. Each of them has a 120-degree phase shift. So imagine I am pulling in 3 different directions with 120-degree shift. What would be the total, or pushing in 3 different directions? What would the total force be in the middle? 0. So if I have 3 currents pulling, this is a physical term. It's not actually what happens, but I just wanted to give you a visual, thing of what happens. If you have 3 exactly equal forces pulling at the same point, the current that is passing that point is what? 0. And since this is 0, it means there's 0 current going inside the ground. And since the current is 0, I don't need this wire at all. So I can eliminate the wire in the middle. So instead of having 4 wires, I can only do it with 3. But there's a catch. You must balance the 3-phase. If one of the phases is a slightly higher current or voltage, it's going to throw it out of balance. You're going to have current going through the ground. So, but in a 3-phase system, we always, when we generate in a Y connection, we only have 3. That's the reason all these transmission lines, you can see there are 3 wires going together, set of 3 wires, not 4 wires. the wire actually you see on the top, the very top, sometimes that's for lighting, or it's for lighting to, hit it and ground it. Sometimes it's actually for, other purposes, like if you want to run another single phase to be able to run the street lights or something like that. The load connected between each phase, if we want to find the power, SLN is going to be VLN RMS, I line RMS, and the total power is going to be 3 times of each power. So the total power, S total, is going to be 3 times the power of each phase. I'm going to call this 3S of phase. Now, using the Ohm's law, I line would be equal to total power over 3V line to neutral, and therefore we can find the line current here as well. Now, this is a simple example. For a 208 Y 120V 3-phase 4-wire system, which has a power of 36 kilovolt amps, as you remember, we measure apparent power in volt amps. We measure reactive power in volt amp reactive, and we measure real power in watts. So watts, volt amp reactive, and apparent power is in volt amps. So kilovolt amps. This is 36 kilovolt amps, or 36,000 volt amps, divided by 3 times the voltage of each phase. And what is the voltage of each phase? It's 120. So 36,000 over 360, because it's 3 times 120, gives us 100 amp. Now, in a Y-connected system, I line is equal to I phase. So if in the question I ask for I line would be also equal to 100 amps. Let me give you this as a question. It's going to be actually an interesting question. Yeah, I actually just give me 1 second. Okay, let's go back. I want you to solve this. Now, for a 480Y 277 3-phase 4-wire system, we want to find I line RMS when the total load is 36 kilovolt amps. Did anyone solve it? What is the current? What did you get? Perfect. Great. Thank you. So again, I line would be equal to S total over 3 times V phase, and V phase is 277. Again, the right one is the phase voltage, the left one is the line voltage. And keep in mind, always the phase voltage is lower than the line voltage. So here, it's going to be the total over 3 times 277, which is 831. Now, the current here is going to be 43 amps. Now, what is the conclusion here? The first one, we got a current of 100 amps. The second one, we got a current of 43 amps. Which one is better? Which load is better? Which motor is better? So both of them have the same power, which is 36,000. So both of them are exactly the same in the output. The thing is, in a transmission system motor, all the time, the power loss is V square over R or I square R, okay? Depending on the resistance, okay? Now, which one do you think is better, higher voltage or higher current for a lower loss? It's better to have a high voltage or a high current. Which one has a better? So imagine both of these motors have a similar resistance of 10 ohms, okay? Which one increases faster, the lower equation or the high one? The upper one, the lower one, obviously. That's the main reason we use transformers in a generation side. We increase the voltage to several 100,000 volts, and we reduce the current, okay? It's always to have a higher voltage, lower current for a lower loss. Now, these two motors have the same output power. One of them requires 43 amps, but 277 volts. The other one is 100 amps, okay? Now, another thing to keep in mind, what was the voltage of the first one? 120. And how much current did it require? 100. Second was 277, and it's half the. So if I want to replace this only in the loss, you can see that there's a huge difference on the amount of loss. Now, what does loss translate to? Heat. Perfect. And the last thing that you want in a motor is to get hot, because it's going to melt. It's going to destroy your motor. It's not going to last that long. To prevent that, we have to use thicker wires. Wires are copper, so you're going to make your motor larger, much more expensive, double the cost. Simply by reducing the current, increasing the voltage, we can mitigate and solve this problem. That's the main reason that anything in your house that is over 3-4 kilowatts, you're using a two-phase at least. You're using a 240-volt system, okay? And I'll explain how that works. You're never going to run your stove or your dryer on a electric dryer, not a gas dryer, on a single phase. Never works that way, okay? It's a very thick wire. It's going to be dangerous. So those things, we usually have higher voltage and we reduce current. Is it clear? Okay. So now 43, and I will explain if you want, I can write the equation, it's, out of the scope of this class. You can see that you actually reduce the thickness of the wire by almost 1/4. And you're going to save a huge amount of money. Now, the current and the voltage, the current has the same equations for the voltage, and for the current for each phase, again, it's going to be the same amplitude of the current, same magnitude, but 120 degrees phase shift. So if I draw the current signal, it's going to be exactly the same as the voltage one, but with a different, same frequency, same phase shift, but different magnitude because you have a different magnitude for the current. Now, if I want to find the, let me go back to see. Yeah, I was on this slide. Sorry. Yeah. So as mentioned, 3 currents with the same magnitude, different phases. And as I mentioned before, if I have a Y connection and all 3 phases are balanced, if I add these 3 currents, IA, IB, and IC, since they are all with the same magnitude, I'm going to get a total current. And if I convert that and everything, I get a total current of 0, according to the. So the current going through the ground, if I have a balanced system, is going to be equal to 0. And therefore, as I mentioned, I could completely get rid of this line. Again, this is just a proof. I've converted the phasor to a rectangular form. And when you get that, you're going to reach this equation. 1 minus 0.5 plus j 0.866 minus 0.5 minus j 0.86. So these two will cancel each other. And 1 minus 0.5 minus 0.5 gives us 0. So this would be 0. So the total neutral current is 0. So you may think this is not a big deal. Okay, we are getting rid of one line or one, wire. But imagine the scale when you want to transmit power from, let's say, Amarillo to New York, thousands of miles. You're getting rid of one of your wires, so 25% reduction. Instead of 4 wire, you're going to have like 3 wire, something like that. It makes a huge difference. And it makes everything much simpler. It's not just a wire. You have sagging effects. You have, the poles that the wires go on. So it's a lot of, benefits to that. So in a 3-phase 4-wire system with a balanced load, the neutral conductor carries no current. With an unbalanced load, the neutral current carries some current. And in the worst case scenario, the neutral carries the same amount of current as the most heavily loaded phase conductor. This usually happens when one of the loads is disconnected. And it's a very dangerous situation. Or when 2 of the loads connect to each other. It's very, very dangerous sometimes. That's the reason in some transformers we have a grounding for that, to be able to, safely ground the system and then prevent damage. And we have breakers and systems that protect our grid from that, or the motor. And the motors, usually you have a grounding, which is on the stator of the motor outside, and you can, most motors, when you bolt them, you're actually grounding them as well. But larger motors, you need to be able to ground them. So if something goes wrong, one of the phases is disconnected, the additional current will go through the ground and you'll be protected. Now, and that when it connects to the ground, actually it creates a spike in the current, and the fuse or the breaker would, just pop. Another type of connection is called a delta connection. It's mainly used in loads. A delta connection, as mentioned, it's connected like a delta triangle. You have the loads on, or each phase on each arm. Now, in a delta connection, it's the exact opposite of a Y connection. In a delta connection, V phase is equal to V line. Okay? But I phase is, or I line, let's say I line, is equal to 3 square root of 3 I phase. So I line is square root of 3 I phase. Why? Because I have the current of each phase coming into this node and going to the line. Therefore, we're adding the phase currents, okay? And by the way, this is I phase and this is I line. So in a delta connection, it's the opposite of a star connection or a Y connection. V line here is equal to V phase because it's the same, but I line is equal to square root of 3 times I phase. And it's going to be the same equations that we had and the same proof that we have had for Y connection as well. Again, the only difference is that in a three-phase delta connection, V line is equal to V phase and I line is equal to square root of 3 I phase. Now here the currents would not add to 0. Obviously, we don't want them to add to 0. And there's a relation between them. And this is going to be the relation between each phase and the currents that we have. And let me get to the final. These are just proofs of the Kirchhoff law and how we add them together. And this is the final equation that we have for that. So for a Y connected and a delta connected balanced three-phase, for a Y connected, and both of them, the power would be same. IL would be S total over 3 VLN, and I load would be S total over square root of 2 V line. What is the difference between the upper equation and the lower equation? The upper one, we're finding the current using the line voltage. The lower one, we're using the upper one we're using the phase voltage, the lower one we're using the line voltage. Now, if in a delta connection, the current is square root of 3 of the phase current, which motor is better? Do we want to have a star motor or a delta motor? Why? So the interesting part is one of them has a higher torque, the other one has a higher power. We always start with a Y connection and then we switch to delta. So even if we have a three-phase delta motor, we usually start it in Y, and I'll explain this in the lab. We're going to have a lab one day dedicated just to three-phase contactors and how we connect them, and how we go from a left turn, right turn, or a clockwise, anti-clockwise, or left turn, right turn motor, how we go from left turn to right turn, right turn to left turn, and how we go from star to delta and delta to star. And I'll explain how it does. But for now, just know that motors start on three-phase on the star connection, and then after like a fraction of a second or 1 second, they go to delta. The reason is because of torque and the power consumption, and I'll explain more about that later on. Just for now, you need to know that the power in a three-phase Y connection is as follows. Current IA, IB, and IC are equal currents of each phase, and it's equal to S total over 3V phase. Or we can write it like this: currents are equal, and it's equal to S total over 3 square root of 3V line. And for a delta connection, again, it's going to be the same. The currents are equal in all three phases, and it's equal to S total over 3 VLN or S total over square root of 3 VLL. Now, just a quick question. I want you to think on something before we move forward. I mentioned about three-phase motors and left turn and right turn. Do you know how we go from a left turn motor to a right turn motor? So to go from that, we have to change the sequence. So instead of going this way, the phases, it should go the opposite way. Okay? So what we do is just flip two phases. So instead of connecting ABC, we do ACB. So flipping two switch, we flip the rotation, and we go from the left turn to right turn. This is the principle of how an elevator motor works. Goes up and down if you're opening or closing a garage. This is how it works in a three-phase motor. DC is completely different. So what we do, we want to change the sequence of the phase, and we do that by simply switching two phases together. Okay, that's it for today. I don't have anything else to add. We don't have any classes on Thursday. I'm going to a conference, and I've already posted the home. Have you seen the homework? You haven't told the next weekend, and I'll post a third set of homework this weekend, so you'll have a week to complete that as well. As mentioned, and a lot of you had requests to go to the job fair. That's the reason I canceled last week. But this week it's going to be a conference, and we're not going to have a class. The exam, we're going to post it for second or first week of March. And I have to, next week we're going to discuss when you don't have any conflict with your other classes, so we can, set that up as well. Before the exam, we're going to have a review session, by the way. The second work, I think it's due this Monday. The due date is on it, isn't it? If it's not on it, I would post it. Yeah, I think it's this Monday. Yeah. Thank you so much, and I'll see you next week.